Hello class. In this lesson we're going to learn about congruence, corresponding parts, and sequences of rigid motions. Before we go on, I'd like you to think of a definition for the word congruent. So what does that term mean to you? And we'll talk about it together. So probably the most common definition that is thought of with the word congruent is things that have the same size and the same shape. And while that is entirely true, that's not a very helpful definition. It's not very rigorous or precise. We don't have any tools really that talk about same size and shape. But what we do have are the basic rigid motions. And we know basic rigid motions preserve distance and angle measurements. So our definition of congruent should involve basic rigid motions. So while this is a good definition for wrapping your head around congruent, it's not really what we're going to use right now. So in middle school, you learned that two figures are congruent if you can get one from the other by using rotations, reflections, and translations. So we're going to use that exact notion to make our own definition. So here is our high school precise definition of congruence. So there is a sequence of basic rigid motions that map one to the other. I'm going to use the word finite here because when you do something an infinite amount of times, sometimes certain properties don't hold. So we want to make sure that we can count how many different transformations we're doing. So that's why the word finite is in there. Okay, so here's a little refresher on function notation for the rigid motions. We already learned these, just read through them, and it'll help you out with this lesson. So here we have a triangle, PQR, that's being mapped onto triangle XYZ. And they walk us through what all the transformations are. So if we follow the function notation here, remember in mathematics, we follow the order of operations, and we start it starts with parentheses, grouping symbols. And you always have to go all the way inside of the grouping symbols to begin with. It's the same with function notation. The first transformation that's being applied is going to be all the way on the inside of the parentheses. So when we write this with function notation, the rotation happened first. So that goes all the way on the inside. So let's highlight that. So here's the rotation. And here we have it in the diagram. And then we reflected over line EF. And finally, we translated using vector V. Okay, and they talk us through it up in this paragraph. So by that sequence of rigid motions, we get triangle XYZ. So let's see if we can fill in the blanks here now. What's the relationship between triangles PQR and XYZ? Well, we know they're congruent because we have rigid motions that map all the vertices onto each other. And we know that rigid motions, they're going to map segments onto segments of the same length and angles onto angles of the same measure. Okay, so we have a correspondence. Whenever we have congruence, we also have a correspondence. And when we make the correspondence, we want to make it so that the corresponding parts have they'll have the same angle measurements when we're talking about angles, and so that the corresponding segments will have the same lengths. So there's a natural way to make a correspondence. So for example, here, we have a rigid motion, a translation that takes triangle ABC onto triangle FED. And so we have three pairs of corresponding angles and three pairs of corresponding sides. So notice that the order is important here in our congruence statement. A and F correspond, so they're both in the first position of the names. B and E correspond, they're both in the second, and C and D correspond, they're both in the third positions. That's very important. Okay, you have to make sure that you put the corresponding parts in the correct order. So here we have a rotation, and now we want to identify the corresponding parts that we have. So what does A map to? When we rotate it, A maps to X, B maps to Y, and C maps to Z. If we do it with the sides, same idea. AB will map to XY, AC will map to XZ, and BC will map to YZ. And so now we want to write the function notation for this rigid motion. So let's go back up to the top, see what it says. It says that we did a 240-degree rotation about point P. What letter do we use for our rotation? Use a capital R. And the two parameters are the center and the angle of rotation. And what's the input here? What's the pre-image? The pre-image is triangle ABC. And what's the image of that, or the output? Now the order is important here. If you have ABC for our pre-image, then we have to have same order, in order of corresponding parts, X, Y, Z. So there we go. So we so far have looked at corresponding parts where all the corresponding parts gave us angles that were congruent and sides that were congruent. But that's not always the case with corresponding parts. We'll get to that in a moment. What's important here is that when all of the corresponding parts are congruent, then the two figures are congruent. When two figures are congruent, then all the corresponding parts are congruent. So that holds in both directions. And when we use this property in proofs, we say this statement in blue. We say corresponding parts of congruent figures are congruent. Now, you can still make a correspondence even if the two figures are not congruent. For example, we can have something called a dilation. These are similarity transformations. And so here we have two triangles that are not congruent, but we can still say that there's a correspondence between them. We can say A corresponds to J, B corresponds to K, and C corresponds to L. So read through this, and just note that correspondence does not have to be from a congruence. That's what I'm getting at. But when you have a congruence, then there's always a correspondence that's appropriate. So this problem, I want you to give it a little bit of thought. So pause the video, and I want you to figure out, see if you can find two quadrilaterals and with a correspondence so that the corresponding sides are congruent, but the corresponding angles are not congruent. So see if you can draw two figures that satisfy these conditions. Okay, so here's my solution. It's not the only right one. We have a square on the left here, and we have a rhombus on the right. And this rhombus is not a square. So I corresponded all of the vertices, A to J, B to K, C to L, and D to M. And note that all of the corresponding sides are congruent. Right? All the sides here are congruent, and all the sides here are congruent in the same fashion. But none of the angles are congruent when we're looking at the pre-image and the, I shouldn't say pre-image, when we're looking at the square on the left and the rhombus on the right. Right? A here would measure 90 degrees, but J would be an acute angle, so it's not 90. B is 90, K is obtuse, so they're not congruent, etc. Okay, so here is one where we have a correspondence, but not a congruence. But we can still talk about how the sides relate to each other. So each side here is double the length of the corresponding side in the smaller triangle on the left. How can we fill in the blanks there? So for example, if we take length AB and double it, what do we get? We get XY. See if you can fill in the other blanks there. Hopefully you got BC and YZ, and CA and ZX. Now, just because you don't have the same order as I do doesn't mean it's wrong. You could flip the order here and say C, B, and Z, Y, and that's still correct, as long as your corresponding parts line up. And finally, we have a sequence of 3 rigid motions. We want to answer some questions about it, about this sequence. So first of all, what is the sequence? What happened here? See if you can name the 3 transformations in order. So first, we reflected triangle ABC, and then we translated it, and then we rotated it. Okay, that's a nice informal sequence that we have, but let's be a little more precise. Let's use function notation. So remember, we start from the inside and go out. So what's the first thing that happens? We have the reflection. For reflection, use a lowercase r. And what's the one parameter? The one parameter is the line of reflection. We have line DE. You can go say segment DE, because every segment is contained in the line. Okay, and then what happens in our sequence? We translated, so we use a capital T, and what's the parameter there? A vector. You can say vector B prime, B double prime. And then finally, we rotated. Remember, we can, this point is A double prime and A triple prime, because when you rotate, that center of rotation stays invariant. So we rotated around point A double prime. How many degrees? Well, they tell us that the angle here, they tell us this angle, C double prime, A double prime, or A triple prime, so they're the same. C triple prime, they tell us this angle is 100 degrees. But be careful. Which direction are we going? We're going clockwise. So we have to say negative 100 degrees. So be careful there. So now let's identify our corresponding sides and corresponding vertices. So side or segment AB maps to segment A triple prime, B triple prime. And we have similar results for the other 2 sides. And what about the vertices? A is going to map to A triple prime, and B and C are similar. And so what's our triangle congruence statement going to be? Make sure we put the corresponding parts in the same positions. So we have triangle A triple prime, B triple prime, C triple prime. In this lesson, we learned about congruence, corresponding parts, and sequences of rigid motions. Thanks for watching this video.